Hi there, my name is Jon Zabalaga and I am a PhD student at the Technical University of Munich and a visiting researcher at Carnegie Mellon University. Today I'll be presenting PHODCOS, a Pythagorean Hodograph-based differentiable coordinate system. This is a joint project with my collaborators and colleagues Fausto Vega, Zbigniew Xir, Zachary Manchester and Marcus Rill. Our motivation comes from trajectory optimization and predictive control for autonomous vehicles such as rockets, spacecrafts or satellites. When doing so, we focus on a very specific subset of approaches, namely path parametric methods. As its name suggests, these methods are characterized for relying on a parametric path. This path is described by a function that maps an auxiliary variable to the Cartesian coordinates of the path. During this talk, I'll refer to this auxiliary variable as path parameter and I will denote it by Xi. The fundamental principle underlying such path parametric methods is to project the system dynamics from a fixed coordinate system to a moving frame attached to the parametric path denoted by capital R. The spatial coordinates resulting from this projection, the progress along the path shown in brown and the orthogonal distance to it shown in green and blue, are very appealing for motion planning and trajectory optimization. This is because they allow to embed the geometric features of the environment into the underlying decision-making algorithms. To conduct this spatial reformulation from the Cartesian coordinates in the fixed frame into the spatial coordinates in the moving frame, state-of-the-art methods rely on the Fresnel frame. Before discussing the advantages and the limitations of the Fresnel frame, we need to understand how it is defined. If we look into its equations, the equations that describe the components of the Fresnel frame, we realize that all three components rely on the path function and its spatial derivatives. Here, the spatial derivatives are given by the apostrophe and refer to differentiating with respect to the path parameter Xi. Further down the talk, when I refer to the standard time derivatives, I'll use the normal notation with a dot. Anyway, getting back to the Fresnel frame, as I was saying, we see that all three components depend on its path function and its spatial derivative. If we look into its angular velocity, we see that the Fresnel frame only evolves in the first and the third component, and it does not evolve in the second component. Moreover, if we look into the rates of the angular velocity, we realize that they are associated to the torsion and the curvature. On top of that, if we look into the expressions of the torsion and the curvature, we also see that these are also dependent only on the path function and its spatial derivatives. So the key point, the most important point here is that the Fresnel frame is only dependent on the path function and its derivatives, and therefore it's analytically extremely simple. This is the main benefit of the Fresnel frame and explains why it has become so popular among the controls, robotics, and space community. However, this analytical simplicity does come with its own disadvantages. First of all, it shows a singularity or a discontinuity when the curvature vanishes, or in other words, when the path becomes a straight line. And this is clearly depicted by the figure shown at the bottom of the slide. In here, we see how the Fresnel frame evolves from a counterclockwise to a clockwise rotation, and once the transition occurs, we see how the second and the third component abruptly flip, showing a clear discontinuity that might render problematic in decision-making algorithms. On top of that, we also see how at the very specific instance where the transition occurs, the Fresnel frame itself is not defined, so it shows a singularity. Secondly, the Fresnel frame is also characterized for having an undesired twist with respect to the first component, and this might also introduce additional nonlinearities in the numerical routines, which might result in numerical issues. To somehow showcase this undesired twist, we can look into the bottom right side of the slide, where we compare the Fresnel frame to the rotation minimizing frame, and we see how the Fresnel frame somehow shows this undesired twist with respect to the first tangent component, while the rotation minimizing frame kind of shows a more natural motion along the path. So these two disadvantages motivate our work and motivate PHODCOS basically, and kind of in order to overcome these limitations, we present the method in our paper. Specifically, in this work, we try to answer the following research question. The research question states as follows. Is it possible to formulate a singularity-free, continuous, and differentiable coordinate system by relying on an exact and efficient path parametrization? This might sound like a lot of buzzwords put together, but in order to kind of convey the message in this question a bit better, let's decouple it into three different parts. First, we want our coordinate system to be singularity-free, continuous, and differentiable. This is because we want to use our coordinate system in optimization-based or machine learning-based algorithms, and these kind of algorithms usually require gradient information, so first order and second order derivative information. In order to ensure that this information is retrievable and also nice, we need to fulfill all these three properties. Second, we want the coordinate system to be exact in the sense that we want the coordinate system to match the input or the reference curve that the user provides us. And last but not least, we want the algorithm or the coordinate system that we present to be efficient for the obvious reason that we don't want to add an additional overhead to our computer. To answer this question, in this work we present PHODCOS, a Pythagorean Hodograph-based differentiable coordinate system. Our method takes a parametric path as an input given by the user and associates a coordinate system to this parametric path. This coordinate system is characterized for having multiple properties which might render extremely appealing to the user. First of all, this coordinate system is differentiable in the sense that all the functions that are involved in the description of the coordinate system are C2 and therefore can be used with optimization and machine learning based methods. Second, it's computation-free in the sense that the computation from the input to the output relies on analytical and closed-form equations, and therefore there are no numerical routines or iterative methods involved in the conversion. This implies that our method is extremely lightweight and can be computationally free. Third, the conversion algorithms has a bounded conversion error. This means that we guarantee that the coordinate system will be within a tolerance that the user will provide us, and we provide guarantees on how fast this approximation happens. Fourth, the coordinate system is geometrically rich in the sense that beyond providing the coordinate system itself, we provide additional information that also might be useful for navigation. For example, we provide the arc length, the curvature, the torsion, and many other geometrically meaningful functions as closed-form solutions, which can be, as I said, very interesting when designing navigation or decision-making algorithms. To achieve this, to basically achieve PHODCOS, our method relies on three main ingredients. First of all, we identify the appropriateness of Pythagorean hodograph curves as a backbone of representation for our coordinate system. Second, we present a C4 Hermite interpolation methods that allows us to obtain the coefficients that describe the Pythagorean hodograph curves. And third, we put both the PH curves of the Pythagorean hodograph curves and the C4 Hermite interpolation together within an iterative algorithm that ensures that or somehow contains convergence guarantees as mentioned in the previous slide. What I will do in the upcoming 3 slides is I will get into the details of each of the ingredients, and I will provide further details on how these are formulated. That being said, let's get started with the first ingredient. The first ingredient consists of identifying Pythagorean hodograph curves, or PH curves, as the appropriate representation for our coordinate system. PH curves are a very broad and complex topic, and due to the time limitations of this presentation, I will only provide a very brief overview. Formally, PH curves are defined as a subset of polynomials whose parametric speed is also a polynomial. This might sound like an empty definition, and what it practically implies is that the arc length and other geometric properties are given in closed-form expressions. Putting it in a nutshell, a PH curve is fully defined by a set of coefficients, and once we've got these coefficients, not only can we rebuild the PH curve, but we can also obtain the polynomial expressions that define multiple geometric properties. Among these are the position, the moving frame, the angular velocity, the curvature, the torsion, the arc length, and many others. Using these geometric properties, we will be able to reconstruct our coordinate system. This raises the obvious question of how do we find the coefficients that we specifically want according to the parametric curve that the user provides? In other words, how do we find the coefficients? To answer this question, we have to move into the second ingredient. The second ingredient is a C4 Hermite interpolation, and it's the most important part of our algorithm. The algorithm will be introduced in the third ingredient, but first of all, before we move into the third ingredient, we have to spend some time in understanding how we conduct the C4 Hermite interpolation. In here, what we do is we take the parametric function provided by the user and we chop it up into n segments. Once we've got the n segments, we take the first 4 derivatives at the beginning and the end of each of the segments. This derivative data is fed into the algorithm, which I will present in the third ingredient, and out of the algorithm we will obtain the pH coefficients. As I just mentioned in our previous slide, in the first ingredient, once we've got these coefficients, we will be able to rebuild the coordinate system. Notice that when referring to the fact that it's C4 Hermite interpolation, we are taking position, velocity, acceleration, jerk, and snap data at each of the segments. Some of you might be wondering why C4 Hermite interpolation and why not C3 or C5. The answer to this question is mathematically involved, and in here I'll just provide the overview or the overall mindset. The idea is that we want our coordinate system to be C2. We want to have the ability to obtain the first and the second order derivatives. This is because we want to use it with optimization and machine learning methods where gradients are commonly needed. In order to ensure that we've got a moving frame and an angular velocity, this means the coordinate system that is C2, and we follow the algorithm somehow backwards, we end up realizing that we need the position function to be C4. For this reason, we do C4 Hermite interpolation. If you are interested in the further details of this reasoning, I suggest that you read the paper. After kind of introducing the pH curves and the C4 Hermite interpolation that we use to calculate their coefficients, we are ready to move on into the third ingredient, where we will show the overall algorithm. In the third ingredient, we put the first and the second ingredients together and we present the algorithm. As I've been mentioning along this talk, the idea of this algorithm is that the user provides us with the analytical curve and a desirable tolerance. Then we iteratively conduct the C4 Hermite interpolation that I just introduced. We calculate the error, and if the error is beyond the tolerance, it's bigger than the tolerance, we augment the number of segments. This way, we keep on augmenting the number of segments until the coordinate system or the obtained converted form is below the desired tolerance. This ensures that the converted coordinate system will always fulfill, or we will always be within the limits provided by the user. Just to be clear here, as we've already mentioned before, the most important part of this iterative method is the C4 Hermite interpolation that we've just defined in the second ingredient. I also want to highlight that in the paper we prove the approximation error by a factor of 6 in the step size, and we kind of this way know how long and how fast we are going to converge into the desired tolerance. This not only ensures that we will be below the desired tolerance, but it also ensures that we will get there within a bounded amount of time. So having defined all three ingredients of our method of PHODCOS, now we are ready to show how this will be used in a practical example. To do that, we conduct a tutorial example over the Near Rectilinear Halo Orbit, or the NRHO, associated with the Lunar Gateway. This orbit is characterized for having a high eccentricity and exemplifies how other frames, such as the Frenet frame, might be numerically problematic or ill-conditioned. Our analysis is divided into two parts. First, we will associate PHODCOS to the orbit, and second, we will create a trajectory optimization problem showcasing how our coordinate system can be used in gradient-based decision-making algorithms. First, we associate PHODCOS to the NRHO. The obtained moving frame is depicted in the left-hand side of the slide. In here, you clearly see how the moving frame associated to PHODCOS moves along the NRHO. The respective parametric speed and angular velocity of the obtained coordinate system are given in the right-hand side of the slide. Having obtained the PHODCOS coordinate system for the NRHO, now we will move on to the second part, where we will exemplify how this can be used in a trajectory optimization problem. In here, our goal is to make a lunar lander navigate from the surface of the moon back to the NRHO. To achieve this, we model the lunar lander as a gimbaled rocket. The system dynamics resulting from this modeling are transformed from a time domain, from a temporal domain into a spatial domain through our coordinate system. Once we've got the spatially based system dynamics for the gimbaled rocket, we model or we create a nonlinear program as a backbone for our trajectory optimization problem. This nonlinear program, as its name suggests, is non-convex and has got multiple bounds in the controls as well as in the states. We test this trajectory optimization problem from different initial conditions located at different spots at the surface of the moon. The obtained trajectories, as shown in the top right side of the slide, clearly showcase how the trajectories converge from the surface of the moon back to the NRHO. The obtained error functions, as well as the control commands, lie within the desired input constraints and kind of showcase how our coordinate system can be used for such trajectory optimization methods or other motion planning scenarios. This brings us to the end of our presentation. And summing it up, what have we done? Well, first of all, we've introduced PHODCOS, a differentiable coordinate system based on Pythagorean hodograph curves. Second, we've presented an algorithm that associates a coordinate system to any parametric curve, characterized for being well-defined in the sense that everything is continuous and smooth, and it's efficient in the sense that everything is given in closed-form analytical expressions. Last but not least, we've showcased how the method's applicability can be used in the NRHO for the Lunar Gateway. I very much appreciate your time for watching this video. I hope you like the presentation, and if you want to dig into the respective code, feel free to explore the repository in GitHub or read the paper in arXiv. Thank you very much and see you soon.